Wednesday session. Our first speaker is Nelson Yokomizo, who will talk about proper time, events, and indefinite order in superpositions of geometries. So,
thank you. Okay, good morning. So I'd like to thank the organizers for the invitation to give this talk here and for the opportunity of attending this conference. So I was asked to give a general overview of indefinite orders and its relation to proper time and other general relativistic concepts to a broad audience coming from quantum information and many approaches to quantum gravity. So, I'll try to be general and introductory. And so this is the title of the talk. So I want to talk about properties of proper time, the definition of events, and indefinite order in superpositions of geometries. And it was stressed yesterday that when we talk about causal structure, one first needs to be very careful about what is the notion of event that is being used. So I'll try to focus on it. And I'll give really some basic ideas both of classical gravity and of quantum information that is needed for that. And then the plan of talk will be like this. I want to start with a general introduction to the area, to quantum gravity phenomenology, for those that are not very used to it. So it will be very basic things to many people here who are already experts on it, but I want to introduce this idea. And then I want to talk about events and proper time in classical gravity first, and then move on to the description of processes with indefinite order. And I want to describe some very concrete models for how the idea of indefinite order can be implemented in gravitational settings. So that's the structure of the talk. And to get started, I want to go back to the 50s, because that's one point in history where you can trace the beginning of this approach, this more phenomenological approach to quantum gravity. So back in the 50s, historically is sometimes described as a low point in the history of GR, not because of the quality of the works that were being done, but because there was not so much activity on the area. So there were just a few researchers, and the groups were like scattered around and not interacting very much, and not interacting with the rest of the community in physics. So they decided to organize a conference with this title, The Role of Gravitation in Physics. And the idea was to discuss how to bring work on gravity and quantum gravity closer to other areas of physics to interact more. Back then in the 50s, there was even a bias against publication of papers in GR and on quantum foundations in the physical review journals. So it was really not the most popular area back then. And so this is the conference, and there's a report from the conference that was organized by DeWitt and Rickles, and there are transcriptions of the discussions. And so it's very nice to see. You can read about the discussions over there. And there was a session on quantum gravity, and Feynman was present, and he was suggesting an approach on how to proceed to make progress on quantum gravity. And what he suggests is that one could just take the same approach that one does in other areas of physics, where you just think of some experiments and then you compute what the result of the experiment should be. And then even if you don't have the experiment already in your hands, you can just say what your theory predicts, what your model predicts, and then you compare with the results of the experiments when they become available. So he was suggesting that, and one thing that he suggested was that one could try and do it by devising some experiment where you would put a mass in a superposition of positions. And the idea was that if you had a superposition of positions for a mass, then there would be a configuration of the gravitational field. In the figure, this is the ball is represented. This is from the report. So the ball is a mass that is put in superposition, and the idea is you can let it interact gravitationally with some other mass, and then let the effect build up with time so that it's amplified, and then you measure some other system that is feeling this gravitational field in superposition. And the idea was, that's what Feynman suggests, that the problem is to be able to tell if we have a non-classical configuration of the gravitational field or not. So it's just compute something for some experiment that you can check if that is right or not. So that's the idea. And so that's how I put it. This is a crucial problem. Just tell whether or not we have a non-classical configuration. And this approach was like, it lay dormant for a while, but in more recent times it was like taken over. And I think there are two main lines where this is happening, this more phenomenological approach to quantum gravity. One is really related to the original idea of having some witness of a non-classical configuration of the gravitational field. And one effect that was proposed for that was the production of entanglement by the gravitational field, because to produce entanglement, you need a quantum system. And if it is a gravitational interaction that does that, this is a suggestion that the gravitational field is in a non-classical configuration. So that's the main idea of this paper, and I think it triggered a lot of activity in this more phenomenological approach to quantum gravity. And of course, you can also try and answer more pointed, more specific questions. And one example is that if you think about a non-classical configuration of the gravitational field, one of the things that the gravitational field describes is the causal structure of space-time. And if you allow for it to fluctuate, you can envisage situations where you have events A and B, that can A be to the future of B, or otherwise there are some possible superpositions of causal structures. So instead of just asking, okay, do I have some non-classical configuration of the gravitational field or not, you can ask more pointed questions like, do I see some superposition of causal structures? And if so, how can I really implement it in some thought experiment with the hopes of getting it done in the lab later? So this line led to the investigation of indefinite causal orders, and it's in this more phenomenological approach, this question is investigated with some phenomenological models. And the idea is to proceed not by constructing a full theory of quantum gravity in this phenomenological approach, but just considering some simple and concrete setups of some quantum gravity models, but not from a general theory, but for very concrete thought experiments. So you can build a phenomenological model just using some simple assumptions on how gravity combines with GR, with quantum mechanics. Usually these models have some indefinite configuration of the gravitational field, like a linear combination of semi-classical states, for instance, superposition of semi-classical states, produced by some superposition of some mass in a superposition state. So I mentioned the production of entanglement, so there are two references here to the BMV experiment, as it's sometimes called, and an example of a process with indefinite order is the quantum switch, and a model for the gravitational quantum switch built upon the idea of exploring some phenomenological model was proposed by Z, Costa, Pikowski, Bruckner, so we have some of the authors here. And I would like to call also your attention to this introduction to the area that was published by Bruno Sado and Natalia Moller, that are my collaborators. And so this is an introduction to the area. I would recommend to anyone who wants to start studying it from the beginning. Okay. And the idea of indefinite order was in more abstract terms pushed by Lucien Hardy since 2005, 2007. So this is a quote from 2007 paper. And the way that he puts it is that in GR, both in GR and in quantum theory, we have a conservative and one radical feature. So in GR, you know, theory is deterministic, but the causal structure depends on whatever is in the space-time, so it's dynamical. And in quantum theory, you tell what the causal structure is in advance. You say, I am in Minkowski space-time or in a Galilean space-time, but the theory is probabilistic. And if you want to build a setup, a framework for combining GR and quantum mechanics, it's likely that you need both radical features in the same theory. So it should be probabilistic. It should admit some causal structure that depends on the matter that is in it. So it leads naturally to the idea of an indefinite causal order connected to the state of matter in the space. So this is the general idea, but then later it was implemented in more concrete terms as a generalization of quantum mechanics using, for instance, process matrix or supermaps, and I want to describe it. So this was the general introduction to this area, and I want to keep in mind this idea of really building simple models, because I want to describe some simple models for indefinite order to make it clear what's going on. And okay, so a few facts, basic elementary facts about classical gravity. First thing is, when we talk about a configuration of the gravitational field, and I'm allowing for some matter fields too, so I have a metric tensor, some matter fields. The physical configuration of the fields is not described by a single for single configuration of the tensor field or the matter field, but a whole class of configurations that are related by diffeomorphisms. It's not a single metric tensor that describes gravity, but an equivalence class of configurations related by diffeomorphisms. Now, one consequence of it is that when you speak about an event in GR, it is not a point in a space-time manifold. And a simple argument for that is if you think of 2 points A and B in the manifold, and suppose that there's some curvature here, but not in A, so you can apply a diffeomorphism. So this curvature here is thrown into A, and the curvature is what describes the behavior of geometry around you. So it makes no sense to speak of A as a physical event because its properties depend on the application or not of the diffeomorphism. So the event is really not a point in a Lorentz manifold, but you can speak of it as a space-time coincidence. So if you think of two world lines, for instance, an observer and some system that it is studying, then you can think about this. When they meet, defines a physical event, this intersection of the world lines. Because this thing is, if you apply a diffeomorphism, okay, you have this curvature here, it's thrown into A, but the coincidence is also thrown into the same point, so you have the same properties of the gravitational field for an event defined in this way. So, and moreover, if one of these systems, let us say, is a lab, and then is a particle that is studied, one of them is equipped with a clock, then you can label this event with the proper time that is read by this clock. So you can think of this event as the coincidence of world lines, and that is labeled by a proper time of one of the labs. And for events described in this operational way, we can introduce a causal structure. You say that B is to the future of A if it is inside the light cone of A, and this notion is invariant under diffeomorphisms. Okay, so a few basic properties about proper time that I want to list now. The first one is that, of course, if you know the proper time along any path, then you know what is the free fall motion of the particle, because a geodesic just maximizes proper time. So this is very basic. And in the weak field limit, this difference in the flow of proper time is given by the Newtonian potential. So the gravitational force described by Newton, you can think of it as the particle just looking for the path that maximizes its proper time. And okay, but then you can get more information about proper time along paths, because you can just look at the difference of proper time between two paths. And then you can ask, what does it tell you about the geometry, this variation of proper time? So if you just compute the first variation for a geodesic, it is zero by definition, because the geodesic is a curve that has zero variation for proper time. If it is not a geodesic, then this variation of proper time depends on the forward acceleration of this reference particle. So this variation of proper time for nearby paths, it is not a property of curvature, it's not a property of gravity itself, but it's more like a kinematical effect because it depends on the forward acceleration of this particle. But then, of course, you can take a geodesic as a reference particle, then this contribution is zero. You can see what happens if you go an order higher. So you compute the second variation of proper time. So what does it tell you? What is the information that is contained in this difference of proper times for nearby paths? So there are two terms here. This is the Singer's formula. So the first one, you see that I'm describing the separation of the paths using this deviation vector here. And so when you look at the effect of it on the difference of proper times, there's a first term here that is a second time derivative of this deviation vector projected along the direction of the deviation vector. So this term is naturally interpreted as some relative acceleration. And again, this is a kinematical effect. This happens also in flat space, is what explains the twin paradox, for instance. And but of course, there's another contribution here, and this comes from the Riemann tensor. So this is really about curvature. So the difference of proper times for nearby paths includes a contribution that describes the curvature of spacetime. So you can read some information of the curvature of spacetime just by looking up proper time changes for nearby paths. And of course, you can minimize this in comparison to that, just taking paths for which psi doesn't vary most of the time. So then you can really just look at the curvature that comes from this variation of time dilations. So time dilation, variations of time dilation are actually curvature. Okay, so let me give you an idea about how we describe processes with indefinite order in quantum mechanics. So I want to use a very simple approach to it, but to think of it as a generalization of quantum mechanics. So in order to describe quantum mechanics with indefinite order, I first want to describe how it looks like, just to give a framework to think about the difference, starting with the notion of definite order. I'm stealing figures from many papers from people in the audience. So here we have a very simple example of a process in quantum mechanics with definite order. So the idea is there are two labs, Alice and Bob, and I'll think of them as closed laboratories so that they are not reading what is outside laboratory, just inside of it, so they have no information of what is outside. And there's a target system that crosses the first lab, Alice's lab, and then Alice performs some operation on it, and then the target system leaves the lab. That's all that Alice knows. And then there's Bob's lab, and it's the same story. So the target enters the lab, that's a coincidence, and then the experimenter operates on it, and then it leaves the lab. So that's what the people inside of the lab sees. And you can ask what is the final state of the target system. And if you are in a situation where there is a definite order, then there's just two possible outputs, because you know that the target has interacted with both A and B. So it can be like this, first A, then B, or like this, first B, then A, and that's all. There are two possibilities, because you know that interaction has happened, because labs have seen the particle. So that's with definite order. Now you can ask, what can happen if there is no definite order, if the causal structure is indefinite? Then you can think of a situation where there's a control bit. You can think of it in the gravitational setting as a state of the quantum space-time you are in. And in one situation, if it is in the state 0, then we have B in the causal future of A. Otherwise, if it is in state 1, have A in the future of B. But of course, then you can prepare this control bit in a superposition here. And in this superposition, what happens is that the final state of the target becomes a superposition of the final states that you have for each order. So you have this kind of superposition controlled by this external bit. And this is what's called the quantum switch. It's this operation where you have the superposition of orders for, is the most basic one, because it's just a single pair of events here. And there are some very general techniques that were developed for working with indefinite order in the more general setups, not only with two events, but with as many as you want, and with the most possible combinations. So I'll not get into this, but the idea is that the main difference between situation with definite order and with indefinite order is that if you have a lot of operations that are applied and you're in a situation where you have a definite order, then you can represent the outcome of all these operations as a quantum circuit, or you have a specified order in which the individual operations are applied. Now you can think of more general contributions that involve superpositions of quantum circuits that gives you a more general situation. And this is in general what this process with indefinite order mean, that you can combine these basic operations in more than one way and then put all of them in a quantum superposition. So this is the basic idea, and you can think of it, of the quantum switch, in a more pictorial way, and by this figure, where you have two slots where you can put some operations that the labs are applying. For instance, this Alice lab and Bob's lab, they do something, and then you can combine these operations in a more general way than in a quantum circuit. So you can think about there's a control bit here, and there's the target system, and what this combination of operations in an indefinite order tells you is that the target may first feel what is done to it in Alice's lab, and then in Bob's lab, or otherwise first Bob and then Alice and then move on. So this is a pictorial representation of this superposition of orders for the quantum switch. So this is the basic idea, and I want to focus on the quantum switch because it's the simplest one. And so I'd like now to move to this phenomenological approach. So I would like to describe some models in the gravitational setting that implement, they are thought experiments, but they implement this quantum switch using the gravitational field. So that's what I want to describe now. I want to describe 3 implementations, and in each of them I want to discuss what is the notion of event that is underlying this specific realization of the quantum switch. So first, there is this work of Z, Costa, Pikovsky, and Bruckner. And so this is a 2019 work. And here the idea is, think of these 2 labs, A and B here, and use this operational definition of event. Think of it as a coincidence of world lines. So there's a target system that will cross the labs. So the event is defined as a coincidence of these world lines, and it can be labeled by a proper time in the lab. So you say, okay, the 3rd tick of this clock tells you that's the event A when the lab sees the target system approaching it. So you can represent the event by the 3rd tick of a clock inside this lab, and I'm saying a lab, but you can think of some quantum system that can interact with the target system. And the same for B, so the 3rd tick of the clock is event B. But then you can think of a situation where you put some mass close to the laboratory B, so that there is some significant time dilation for B, and it can be enough to throw this event B to the future of the event A. You just need enough time dilation for that. You can also think of a situation where instead of putting it close to B, you put the mass close to A, and then it's the other way around. So now it's A that is to the future of B. So you can have these 2 situations just playing with the position of the mass with time dilation. But then you can consider a superposition of this situation and that situation. So you put the mass, it's the Earth here, but you don't need a planet, it's just a way of representing this mass. And if you put in a superposition of 2 positions being close to A or close to B, then you have a superposition of these 2 causal structures. So that's as it seems to me, the basic idea for this implementation. And then, of course, you need to build a setup in which a target system passes through both labs. And there are many ways of implementing it. So there are a few of them are described in this same paper here. And I'll just give you the idea of one of these implementations. So in this case, what we have is it's just part of the figure that appears in the paper. I cut it because I just want to describe this point. And so we have lab A and lab B here. There's a distance h between them, so we have space in the vertical axis and time in the horizontal axis running towards the right. And here's the mass. And initially it is in a definite position. Then you can make it pass through something that partially reflects it, so that it's put in a superposition of paths, the blue path and the orange path. And for the orange path, it is far away from the labs, so you can at first just neglect the effect of time dilation for this one. But for the blue path is arranged so that it is close to the labs and closer to Alice than to Bob, so that Alice has some time dilation for this blue path. And the time dilation here is represented by this orange circle moving a bit to the right. So that's the main effect of time dilation here. And then this is the target system, and you can throw it upwards towards the labs, and it passes through the line that represents lab A, then goes to B, and then comes back. And you can arrange this so that it passes through the point where lab A is with proper time tau A for the configuration where the mass moves through the orange path. So that's it. Now, the same proper time happens a bit later in the coordinate time if the mass moves through the path in blue. So that what happens is that in one case, if the mass passes through this orange path, the target first meets A and then B. And of course, A will not be here in the orange path. But for the other path, it first meets B and then A. So in one case, we have first A, then B. In the other case, first B, then A. But it's important to notice that it's the same proper time here and here for the situation where the target meets lab A. It happens at different coordinates for space in the distinct space-time superposition, but the proper time is the same. So inside your laboratory, the idea is you are the experimenter there, you're inside your laboratory, target comes in, you look at your clock, tau A, you operate on it, it leaves the lab, but for someone outside of it, it is not localized. So this is one implementation, and it suggests an idea of an event in a superposition of geometries that looks like this. It's the same idea as in classical gravity. You specify the event as a coincidence of world lines of the target and of your lab, but it can happen in either one geometry or the other. So it's a single physical event, but it has images on the different space-times in superposition. So you can think about the event itself as having these images in each of the space-times in superposition. And you can also think of it, this is a picture that is very natural in this context. If you have a lot of space-times in superposition here, your physical event is like it's like an identification, like some line threading through these space-times in superposition, but it's just a single event. That's the main idea as I see it. And okay, so I'd like to mention another implementation of the quantum switch. Let me check my time. Okay, and this is this second implementation. It's a work with Natalia Moller and Bruno Assado. And it's a variation of the same idea. So the main basic ideas are the same. The main difference that first we use to implement this quantum switch, one of the agents that really interacts with the quantum space-time, with the quantum region of space-time as I will describe, it crosses this superposition of geometries in free fall. And we use it so that the lab has no way of reading some information of space-time outside of it because it's just free-falling. But it's free-falling in a superposition of space-time, so it looks like intuitively as a superposition of Einstein's elevators just falling through in both space-times at the same time. So that's the idea. And also we have a superposition of geometries that is restricted to a region. I'll describe it. So the idea here in this other setup is to use a superposition of masses, a mass in superposition, but not in a superposition of specific points. So the idea is take some mass and distribute it over some thin shell of some radius r, so that you have Minkowski spacetime inside of this shell and Schwarzschild outside. So this is one of the geometries that we consider, but there's another branch where you took the same mass and instead of just putting it over a single shell, distribute it over two shells, so that the exterior geometry is the same as in the previous case, but the interior geometry is different. And then you can consider this superposition of these two spacetimes with the same notion of event as before. It's like some identification of points in these two spacetimes. So in this case, we have something that looks intuitively like this. So it's the same mass. It can be in one shell or in a combination of two shells, but outside the largest radius among all these involved in these shells, it's the same geometry here. So you can think about this exterior geometry as some definite geometry where you can put some clocks here, classical clocks, synchronize them, and see what the geometry is outside of this region. But there's a finite region where you have a superposition of geometries here because there's a mass in superposition locked within this region of space. And you can think of it as having a Heisenberg boundary here where you have a classical world outside of this region and a quantum region of space-time inside of it, and you can try and read properties of this quantum superposition of geometries inside of this region by throwing things inside of it, seeing what happens, what comes out of it. So that's the idea in this implementation. And I'll just give an idea of how does it work. So I'm representing here the opposite sides of this region. So let's say right and left of it, and the region where the superposition is in between here. So the idea in this setup is to put one agent in one side, to the one side of your shells, and the other agent B and the target system to the other side of it. And then this is Alice. Just let Alice free fall toward the masses that are in the central region. So then it goes inside this quantum region, then it emerges again, but there's a separation of the paths because the geometry inside of this quantum region is not definite. So it takes more time in one case than in the other for Alice to reappear in the other side of these shells. So there's, after Alice has crossed this central region, the lab reemerges in a superposition of paths. So one of the paths emerges first and then the other one. And so in the first path, then we have a proper time tau A when Alice meets the target here. And after the lab comes back to the central region, we start to oscillate because of this mass. Then B comes over and also applies some operation at the target at proper time tau B of it. But then in the other branch, the path of Alice comes out from this central region and also reaches the target at the same proper time and operates on it. So the idea here is that in one case we have first A then B, and in the other case first B then A, but this difference is due to this superposition of geometries in the central region. So this is another kind of implementation. And Alice is the lab that crosses this superposition of geometries, and the lab does so in free fall, so there's no way of getting any information about the exterior geometry. So that's a second implementation. And I'd like to also describe a third implementation. And in this case, it is a quantum switch on a definite geometry and not on a superposition of geometries. And now the main idea here is that if you have a situation where there is a superposition of masses here and some quantum system that is interacting with it, then you can have a equivalent situation where the mass is in a definite position, but the quantum system is in a superposition of positions because this gravitational interaction in the Newtonian limit just depends on the distance between the agent and the mass. So these two situations are essentially equivalent. So you can think about doing some mapping. You can think of it as a change of quantum reference frame, but applying it to a situation like the quantum switch that was originally formulated for a superposition of masses. But then you can think about a similar setup where instead of having a superposition of positions, you have the mass in a definite position, but the agents in a superposition of paths. And so this is another work in collaboration with Natalia Moller and Bruna Sado. And then it's not an exact translation, but it's the same idea under this equivalence. And here we have just describe briefly the idea of this very, remember I'm really thinking about phenomenological models. The idea is to have some very simple configuration to get this done. And the idea here is that if you have some Schwarzschild metric, then you can think about, put some lab at the surface of the Earth, for instance, and then you can think about an agent is just at a height h above surface. It just stays put over there. And there's another agent A here. And this can be prepared in a superposition of paths. So one path goes to the right, the other to the left. And the one that goes to the left goes up to the same height as the agent B, stays there. And the other one that goes to the right stays a little bit near the surface so that there's more time dilation building up, and then it goes up too. So less time has passed for this one. But they are then at the same height. And after they are, everything is at the same height, you can send some target system here that passes through the position of one of the agents for one of the branches, then through B, and then through the position of A in the other branch of the superposition. So they have first A then B, and first B then A in the other path. So that's how you can implement it in a definite geometry. And in order for these to work, you need to let this experiment last for some coordinate time here that is enough for this time dilation to compensate for the time of this travel of the target between the two paths. And you got a condition for this to work, and when you look at this condition, there's something that depends on the acceleration of gravity there, and this comes from that first effect in the variation of proper times that I described in the beginning, but there's also a contribution from curvature here. So there's also a real gravitational contribution to this effect, and of course you could think of a variation of it in which the lab's falling so that you get rid of this first time, and then it would just depend on curvature, right? I'm sorry. So in this setup where where the quantum switch is implemented on a definite geometry, then of course you don't have a superposition of spacetimes. You just have one spacetime. But in this case, we have a notion of physical event that is more like this. So you have this agent here, and there are two paths where it is traveling, and the same proper time can happen at different positions and times and coordinates. And then we have this kind of delocalized physical event. Proper time tau A is the same in these two events, but from someone looking outside of the lab, it looks as if it happens in distinct places in space-time. So we have a notion here that is very different from the notion that we have an event in GR, even though we are in a definite space-time. This is an operational event, and it looks delocalized when you compare with the usual definition of an event in GR. So that's the notion that enters this quantum switch. And of course, you could go on and think about the more general situations where you have a superposition of paths and a superposition of spacetimes, and you would have something like a delocalized physical event in an indefinite spacetime. It would look like this. You can think of it as a single physical event, lab showing proper time tau A as like four distinct stuff in a superposition of paths and spacetimes, but I don't know of any quantum switch that's implemented like this, but it's a natural idea. So let me conclude here. So I'm just started with this notion of operational event as a coincidence of world lines. And then I described what is quantum mechanics with indefinite order and some implementations of the gravitational quantum switch, both with a superposition of geometries and in a definite geometry. And we're saying that the notion of event is the same as in GR. It's this coincidence of two world lines, but then you have more general possibilities due to the superposition of geometries and also due to the superposition of paths. So you can have these events an identification of points in distinct spacetimes and also as delocalized events in a definite spacetime. And this is what is used in these concrete models for the quantum switch. So thank you.
We have time for one quick question.
Thank you. Could you go back to one of the slides where you show the event A in several different spacetimes, or anyone will do?
Like this?
Okay, that's great. Okay, perfect. So let me push you a little bit on your definition of event. You slide between operational definition of event and definition of event in GR. So let me say, so the event there, A in M1, if you calculated the, say, some curvature scalars there, they would be different from the curvature scalars that you would calculate at event A in M2. So I would not then identify those two things. So you could call them A and A primed, but I wouldn't say they're the same event. Can you comment on that?
Yes. So I think that one of the things that there are these different implementation of the gravitational quantum switch, and in one of them you have a different, even the acceleration of the lapse is different in the space-time, so you can distinguish between the space-times. And I would agree with you that you would like to have a situation where you cannot by any means distinguish between the space-times M1 and M2 in the superposition from your lab. And then in the second implementation that I was describing, the lab that crosses this quantum region of space-time is in free fall. So the idea is that you put it in free fall so that it cannot really measure the geometry. But in this situation, I agree that I'm in an approximation where inside of the lab, the tidal effects will not be possible. It's not possible to measure them inside of it. So I'd say that you need a situation where you cannot measure the geometry, or you do not have access to it. Because if you have access to it, then you're measuring the geometry. If the curvature is different and you measure effects of the curvature in your laboratory, then the superposition of geometries is destroyed. So I think that you must really consider an event not just as this identification, but also you need to include what is being measured and what is not being measured. So if you measure the curvature, then the superposition is destroyed. So that's how I think of it. I don't know if that makes. Okay.
Let's thank Nelson.
Okay.